Okay, so we had the 3 examples of inequalities on the board, and you were asked to just describe how you would solve them. Not to solve them, but just to describe it. We'll do this for right now, it's a little dark. Of the 3, does anyone feel like they can generally describe how you would solve that given inequality? I know now you're writing for the middle one. What was your process for solving this middle inequality? Absolutely. Why are we able to just straight up use inverse operations for this first inequality, this middle inequality? What is the characteristic of the equation of the inequality that lets us just use inverse operations? I can't hear you. So it helps that, oh yes, so you got there. There's only one instance of the x symbol in our inequality. If you only have one instance of an x symbol, you can just use inverse operations. Do we have only one instance of x here? No, we can't use inverse operations. What about here? Yeah, so actually for both of these two, we're just going to use inverse operations. Now what those inverse operations are might be tricky. This one we'd have to exponentiate. This one we're going to have to do subtraction and division and the square root, all that stuff. But the general idea would be inverse operations. What are the tricky parts about this one? What are the things that people might forget to do that would result in the wrong answer? Yep. So when dividing by a negative number, the direction of the inequality symbol changes. Absolutely. That's like a common mistake people make. They forget to do that, and then their answer isn't correct. What is the other common type of mistake people make for this middle one? This middle one has a power of 2 on the x. How do we cancel out a power of 2? A square root. When we use square root as an inverse operation, what do we have to do? What is my favorite word in all of mathematics? We have to bifurcate. So bifurcate when using root as inverse. Those are the 2 common ways people would use inverse operations, but still get the wrong answer, because they would forget to change the direction of the inequality symbol, and they would forget to bifurcate when using square root as an inverse operation. Okay? I believe if you actually solve this one, you get no solution. This one has no real solution. There's no values of x where if you plug it in, you'll get a number larger than 10 on the left side. That's okay, that happens sometimes. For the log one, we've already said that we would use inverse operations. What is the tricky thing when you are solving a log inequality that you have to remember to do to not get the wrong answer? So canceling out the log is sort of baked in with the inverse operations. We would do 4 to both sides. We would get some numbers. If you did that inequality correctly, you might get something like x is less than 14. That's not going to be the correct answer, because that answer doesn't consider the initial domain constraints. So that is the phrase I want to really get baked in. Consider initial domain constraints. What does that mean? What does consider initial domain constraints mean?
If it doesn't go to like negative sign.
Yeah, that the log function has a domain that doesn't include negative numbers. So we have to consider this part here, and we have to make sure to include that in our answer. So it's not going to be x is less than 14. It's actually -2 is less than x is less than 14. We have to consider the initial domain constraints. The kinds of functions that have initial domain constraints are log functions, radical functions, and rational functions. Okay? All other functions are just all numbers. Does that make sense? We're still using inverse operations, and we have to consider our initial domain constraints. If you don't, you might make a mistake. This last one, you can't use inverse operations. Why can't you just use inverse operations to solve this inequality?
There's two axes.
Yes. If there are multiple instances of the x symbol, you cannot just use inverse operations. There are lots of things you can do, but you can't use inverse operations. So, what was the general idea that we learned about in class on Tuesday for how we would solve this inequality? So to solve this inequality, you would sketch the graph. You would sketch the graph of this function. You would sketch y equals x minus 2 times x minus 3. I think when you sketch that graph, you would get something like this. How do I know 2 and 3 are where the graph crosses the x-axis? Headphones off, please. Joanna? Okay, so the zeros. Yeah, I can ZPP this and see that they're the zeros. So therefore, this is the sketch of my graph. Oh, and I'm looking for where the graph is above the x-axis, and that would be the solution. So I would get, I get negative infinity to 2, union 3 to infinity. This is the exact example that we did in class on Tuesday. So you already should have notes of this in your notes, because it's what we did. 2 of these examples we would solve using inverse operations, but there are common mistakes people made that we want to avoid. Right? When dividing by a negative, make sure that you change the sign of the inequality symbol. Make sure to bifurcate when you're doing radicals and inverse operation, and consider initial domain constraints. And then there are these types of inequalities that we can't use inverse operations for, but we could sketch or factor or something. Okay? The bottom inequality is categorically different. You were asked to explain why it would be very challenging to solve the following inequality. Does anyone have like a structural reason, a characteristic of this inequality that would make it hard to solve? So first off, there are 3 instances of the x symbol. Now, that doesn't mean it's impossible, right? I can give you a polynomial, and you can maybe sketch the polynomial, and then you can solve it. What about this is uniquely challenging? There are x's that are in like the normal argument place of a quadratic, and then there is an x in the pattern. The left side of this is a quadratic function. The right side is an exponential function. I don't know what to do. If I take the log of both sides, I'll have log over here. And then if I exponentiate both sides, I'll have an exponent over here. And you'll go back and forth forever. You'll never be able to solve this the way we want to. So we can't solve it using algebra, but we can solve it. And there are certain kinds of questions you see on the AP exam and in general that can only be solved using technology, and this is one. So what we're going to do is we're going to look at how to solve this kind of inequality. And we're going to do it with our calculator. So let me pass out calculators real fast. Okay, here are our calculators. Go ahead and grab your calculator, and you're going to graph 2 equations at the same time in the calculator. The first equation is y equals x x squared minus 3x minus 4. That can be your y sub 1 equation. Your y sub 2 equation should be negative 1 times 2 to the power of x plus 1. You're going to graph both of these equations at the same time, and you're going to hit enter, hit graph, and you're going to graph them together. Okay? Call me over when you've done it. We can make sure we're all on the same page. Okay, let's graph it. I think it's x plus 1. Oh, yeah. Alright. Graph them up. Yep, you should get 2 graphs. I think I managed to do my colors the opposite of what the calculator colors are. So that's awkward. My bad. My bad, right? Anaya did it, and for her, the exponential one is red, and the quadratic one is blue. So we'll make 2. Okay? When you graph them, you should get a graph that looks like this. Right? I managed to now even use the same colors as that. In this one, the quadratic one is black. So this side is black. And the other side is red. How can we use this graph to determine when the left side of the inequality is less than the right side of the inequality? What does less than mean physically in a graph sense? In a graphical sense, what does it mean to be less than something else? It means below. So really what we're trying to determine is, when is the black line below the red line? Is there an interval on this graph where the black line is below the red line? I'm not sure where you're getting negative 4 from. Can someone come up here and just literally circle the part of the graph where the black curve is below the red curve? I mean, I claim it's like roughly here. Why is it roughly there? Because if you look at this spot, the red curve is above the black curve. And there are 2 spots where this switches. And what are the names of the spots on graph where a graph crosses another graph? Intersections. And so theoretically, all we have to do is figure out the intersections of these 2 graphs. And if we figure out what those intersections are, we'll be able to find the interval between those intersections where the black graph is below the red graph. Does that idea make sense? That's what you're doing when you solve an inequality. You're figuring out where things are intersecting with each other, right? And in this case, we're figuring out where the black graph and the red graph are intersecting, but we don't want to use algebra because it would be uniquely challenging. Does anyone remember how to find intersections on the TI-84 calculator? I'll go ahead, I'll give you the values. Those are the x and y values of the points of intersection, right? So we would get negative 0.7, I'll round to 3 decimal places, 50, and we would get 1.639. Those are the x values. Try to find them. You would hit the second trace button, the calculate button, right? Second trace. And you go down to intersection, and you hit enter, and you scroll along the graph to roughly where the intersection is. You want to be close by the intersection. And you would hit enter, enter, enter. Just hit enter, enter, enter. There you go, enter, enter, enter. Denise, what x value did you get right there? Please be loud enough that people in the room can hear you.
-0.4.
Yeah, you got this exact value right there, right? So you find both of your points of intersection. Now in this case, is the black graph below the red graph between these points of intersection or outside these points of intersection? Between. So for our interval from where this is, from where the left side is less than the right side, it's just this interval. Everywhere between these x values, right, these are the x values of the interval, the black graph is below the red graph. We just found the solution of inequality. We didn't do it using algebra and solving and inverse operations. We did it using a technology, a graphing calculator. But the idea at the heart of it is the same. We found where these graphs intersect, and we're thinking about where one is below the other. Does that make sense? Can I get a 3, 2, 1 on like what we just did to solve this? Okay, let's do one more to kind of make sense of this. Make sure we're all on the same page. Okay? So here is what we're gonna graph. Again, we have a log on the left, we have an x on the right, two x instances, very challenging to solve. So let's graph. We're gonna graph, I'll try to do this the right way now. Y equals log base 2 of negative x plus 3. And we're going to graph y equals negative 0.2 x plus 1. And I'm going to graph these with my own TI-84 graphic calculator. So log base 2 of x plus 3, and then negative 0.2 x plus 1, and I graph. Okay, that's what it looks like to me. Okay. On the screen that we have right here, how many points of intersection do we see? 1. But who thinks that there actually might be more than one point of intersection for these two graphs? I do. Why do I think that there might be more than one point of intersection for these graphs?
On the left side?
I think on the left side. See how these two lines look like they're approaching each other? The blue one's concave down. If it's concave down, it's got to keep sloping downwards. The red one has no concavity. It's going to be consistent. They have to intersect. So the question is, how do I find that intersection? There's a couple ways to do it. I could hit the window button, and I could just make my x min be a little bit less. I could make it be like negative 15. Let's try that. Negative 15, right? And then I'll hit enter, I'll hit load graph, and I'll see if I see the intersection. Okay, that kind of works, but I'm not sure. I could try zooming out, right? I can just zoom out. But a lot of times when you zoom out, it zooms out really far and it's also hard to see. So zooming out might work, the window might work. There's a third way, and I wanted to show you this way because it's very, very useful. If I have my standard zoom, everyone hit not the calculate button, but just the trace button. Just the normal trace button. Trace. And if you trace along this curve, the blue curve, right? And you get to the edge of the window, watch what happens when I keep hitting left. It keeps going. So you can nudge the window a little bit to one side or the other by just tracing along. And now, I'm very close to my point of intersection. So I would do second calculate, intersect, enter, enter, enter. And that's my point of intersection, negative 16.384. So I'm finding points of intersection. Holy, right? So I found, I broke it. I found negative 16.384. Go ahead and find the other point of intersection for these two. There's not always 2 points of intersection. There might be 1, there might be 3. Go ahead and find the other point of intersection. Oh, I found it. Oh, I did. Did you get the same point? Okay. Back to, so we use the calculator to find these points of intersections. If we think about the actual question we were asked, we wanted to find when the log function is greater than the linear function. In the given graph that we have, is the red or the blue curve the log function? Which one's the log function, red or blue? Blue. I wrote it in blue, but also it's the curved one. So is it going to be between these values or outside these values that the log function is greater than the linear function? Between. Because the blue one is above the red one for between those values. So in that case, we would get this. What if it had been the opposite way? What if it had been, instead of the log function greater than the linear function, what if it had been the log function less than the linear function? What would our answer have been? Let's look at the graph. So here we go. What's going to happen with this blue log line as it goes further? Like, will it ever stop going to the left? No. So the left part of our interval would be negative infinity to negative 16.384. And there's another part of this interval, right? Because it switches again right there. So we're going to have union. And what value would go right here? What value would go right here? Yeah, guys, I need a, come on, I'm doing all of it. I need a little bit from you. Right? A little bit more than just like, yeah, the 1.399. Or 1.339. And the question is, do I put infinity here or no? Oh, Denise already said no. Why don't I put infinity here? Because it stops. It's got a vertical asymptote. I have initial domain constraints. What are the initial domain constraints for this going to be? What value of x makes that thing become 0? 3. So it's going to stop at 3. That would be the answer. I still have initial domain constraints. I might still, like, I'm not bifurcating and stuff like that, but I still have to think about initial domain constraints. I have to think about what the graph is telling me. Now, this is if we were saying that the log function is greater than the linear function. This is if we're saying the log function is less than the linear function. We actually made a big error. Does anyone know what the big error is that we made? What's the big error that we made? Can someone read that inequality verbally, loudly? It's greater than or equal to. It is not greater than. It is greater than or equal to. So some things have to change in our answer. Because this symbol means less than. Or greater than, I guess, in that sense. What symbol should we be using here? What? What the integral notation for greater than or equal to? Remember that? So for both of these, it would have to be that, because we have to include those values. For the bottom one, there are 4 parentheses currently given. How many of those parentheses should be turned into brackets to be correct? The options are 0, 1, 2, 3, or 4. How many? Shelton said 2. Alyssa says 1. Alyssa, come change the one that you think should be changed. Careful of the cord, because I already took over it, and I'm really athletic. Thank you. Which symbol should be different? So that one has to stay as a parenthesis. Why does this one have to stay as a parenthesis? Where did we get the 3 from? It's the vertical asymptote. So this one has got to stay as a parenthesis. Which other one has to stay as a parenthesis? Negative infinity, because it can't be equal to negative infinity. But these middle ones, because these middle ones come from the inequality solving part, should be that. We haven't really seen integrals like this that much. They don't really show up when you work with like normal functions. They more occur when you have inequalities. Okay? So we're using our calculator, we're graphing, we have to think a little bit, I'm looking for spaces of above and below. I'm looking for intersection points. There might be 1 intersection point, there might be 2, there might be 3, there might be 4. I don't know. And we can kind of summarize this. I'm going to leave this on the board for a little bit so you don't have to write it down right now. But just to summarize, you're trying to solve a complicated equation or inequality. Notice, I included equations here. If you were asked to solve a complicated equation, the only difference is you're not looking for integrals. You're just looking for the intersection points. Okay? So, we treat the 2 sides of the equation or inequality as separate functions. That's why we graphed y1 and y2. We graph each of them independently. y1 equals the left side, y2 equals the right side. We look for points of intersection between the graphs. The points of intersection are the solutions for an equation, or if we have an inequality, they're the cutoff values of the integrals. And then finally, as a reminder, you can use the table to find when the intersections might occur if you don't see them. You can zoom out, you can trace and scroll, lots of different options for how to find those points of intersection. You feel okay about this? I'm going to stop that video. Did you know you were on video, dudes? World famous.